Hello students, welcome to EPG Pathshala. I am Dr. Anjali Sharma from University of Delhi. Today we are going to discuss about the module Tensors from paper Mathematical Tools for Materials. So students, let us see what we are going to learn in this module. In this module, a new perspective is given to the idea of vectors which are related to the properties of physical quantities under rotation. The tensor notation is introduced, which is a big help in the study of rotational properties. Next, the Einstein summation convention, which simplifies a formalism, is introduced. Vectors are defined from the perspective of their properties under rotation in the three-dimensional physical space. The idea is then generalized to tensor of second and higher order ranks. Further classification of physical quantities on the basis of their behavior under inversion of the coordinate axis is also discussed. In this tensor notation, the indices play a very important role, and it is demonstrated how playing around with the indices may lead to the significant results. Two very special tensors, the Kronecker delta and the permutation tensor, are introduced and their properties are discussed in detail. Next, the certain vector identities are written down and it is demonstrated how the tensor methods greatly simplify the derivation of such identities. Now let us see rotation and vectors. So far we have studied two kinds of physical quantities, scalar, which need only a magnitude to describe them, and vectors, which in addition needs a direction to specify them completely. There are many physical identities that do not fall in either of these two categories. They require more than one direction to specify them, so as to say. We now wish to generalize our ideas to include such objects in our study as well. For that purpose, we first reintroduce vectors from another point of view, that is, through their transformation properties under rotation in the physical three-dimensional space. This is most satisfactory way of introducing vectors than simple as objects having both magnitudes and direction. This defined when can be easily generalized to include other physical entities that we have in our mind. Consider a coordinate system OX, OY, OZ. Let the coordinates of a point P in this system be x, y, z. What will be the coordinates of a point in the rotated coordinate system OX dash, OY dash, OZ dash? The origin has remained the same, only the orientation has changed. Let the coordinates of a point P whose position vector is r be x, y, z and x dash, y dash, z dash in the two system. Then r vector is equals to x I cap plus y j cap plus z k cap is equals to x dash I dash cap plus y dash j dash cap plus z dash k dash cap. The tensor notation. The notation can be greatly simplified by representing the three axes as x1, x2, x3 and x1 dash, x2 dash, x3 dash instead of x, y, z and x dash, y dash, z dash respectively. Unit vectors are represented by E1 cap, E2 cap, E3 cap and E1 dash cap, E2 dash cap, E3 dash cap. Then r vector is equals to x1 E1 cap plus x2 E2 cap plus x3 E3 cap and it is further equals to x1 dash E1 dash cap plus x2 dash E2 dash cap plus x3 dash E3 dash cap. Take the dot product of both sides with the unit vector E1 dash cap. So r vector dot E1 dash is equals to x1 E1 cap dot E1 dash cap plus x2 into E2 cap dot E1 dash plus x3 into E3 cap dot E1 dash cap is equals to x1 dash into E1 dash cap dot E1 dash cap plus x2 dash into E2 dash cap dot E1 dash cap plus x3 dash
into E3 dash cap dot E1 dash cap. X1 dash is equals to X1 into E1 cap dot E1 dash cap plus X2 into E2 cap dot E1 dash cap plus X3 into E3 cap dot E1 dash cap. Denote the direction cosines EI dash cap dot EJ dash cap between XI cap XJ by AIJ. Then x1 dash is equals to a11 x1 plus a12 x2 plus a13 x3. Similarly, we have other two equations also. So together they can be generalized as xi dash is equals to summation over j equals to 1 to 3 of aij xj.
The transformation from the unprimed to prime coordinate system is a linear homogeneous transformation. There are 9 coefficients aij in all. However, all the 9 are not independent. For transformation in a plane, say the xy plane, out of the 4 coefficients, there is only one independent parameter, the angle of rotation. In the 3 dimensions, there are 3 such angles called the Euler angles.
Since under a rotation the magnitude of a vector does not change, then we have r square is equals to r vector dot r vector equals to x1 square plus x2 square plus x3 square equals to x1 dash square plus x2 dash square plus x3 dash square, which implies that summation over I equals to 1 to 3 xi equals to summation over I equals to 1 to 3 xi dash dot xi dash equals to summation over I equals to 1 to 3 and summation over j equals to 1 to 3 aij xj into summation over k equals to 1 to 3 aik xk, which implies that summation over I equals to 1 to 3 xi is equals to summation over 1 to 3 into summation over j equals to 1 to 3 aij xj into summation from k equals to 1 to 3 aik xk. So on comparing the coefficient of various terms, we have summation over x equals to 1 to 3 aij into aik is equals to 1 if j is equals to k. Summation over I equals to 1 to 3 aij aik is equals to 0 if j is not equals to k. So this implies that summation over I equals to 1 to 3 aij aik is equals to del jk. The symbol del ij is represented as Kronecker delta. It equals unity if I equals to j and 0 if I is not equals to j. Since the expression is symmetric between I and j, this leads to 6 conditions on the 9 coefficients aij. Thus, only 3 of them are independent.
Now let us see the Einstein summation convention. The notation and the writing can be further simplified by using what is called the Einstein summation convention. Under this convention, an index subscript can appear only once or twice. Each index takes the value either 1, 2 or 3. An index that appears once in a free index. Every free index represents a set of 3 equations for 3 values of the index. An index that appeared twice is a dummy index, and the index is understood to be summed over so that every such index represents a sum of 3 terms. One dummy index can be freely replaced by the other. Thus, summation from I equals to 1 to 3 aii is equals to aii equals to ajj equals to a1 square plus a2 square plus a3 square. The free indices must match on the two sides of an equation and each term of an expression.
Thus, summation over I equals to 1 to 3 AI into AI is equals to AI into AI equals to AJ equals to A1 square plus A2 square plus A3 square. Using this simplifying notation, we can now write down xi dash equals to aij xj, xi is equals to xi dash, aij aik is equals to del jk. Matrix representation. Many of the equations above can be written in an even simpler form in terms of matrices. If we put the coordinates of a point in the form of a column matrix, that is x equals to x1, x2, x3, then we define coefficient matrix as A equals to A11, A12, A13, A21, A22, A23, A31, A32, A33. Then the above equations can be written as x dash equals to Ax, x transpose x equals to x dash transpose x dash, A transpose A is equals to I. The symbol x being used for the set of three coordinates and not for the abstract vector which is represented here. The superscript T refers to the transpose of a matrix and I refers to the unit matrix. The matrix A is an orthogonal matrix, that is A transpose is equals to A inverse. Rotations are represented by an orthogonal matrix. This is true of rotation in any number of dimensions. The inverse transformation is given by A inverse x dash equals to A inverse Ax equals to x, which implies that x is equals to A transpose x dash. Thus, the inverse transformation is given by the transpose of the coefficient.
Now let us see the rotations and tensors. So far we have studied the properties of the position vector under rotation. We now extend the same idea to other physical quantities and thereby define tensors of second and higher ranks as physical quantities having more complicated transformation properties under rotation. We first redefine a vector in terms of its transformation property under rotation. The position vector transforms according to the equation xi dash equals to aij into xj. Now remember the rule, a free index is summed over. We now define a vector to be any set of three physical quantities which transform under rotations in the same manner as the position vector. Thus, if A is a vector, then its component in the two coordinate systems are related by A dash I equals to Aij, Aj. A scalar phi is a physical quantity which is invariant under rotation, so phi dash is equals to phi. Every physical quantity can be categorized as belonging to the sets of scalars and vectors. There are other transformations in a more complicated way under rotation. Any set of 9 physical quantities which transform in the following way under rotation are said to be a tensor of rank 2, like Ti dash, like Tij dash equals to Aik, Ajl, Tkl.
Moment of inertia, stress and strain, and Maxwell's stress tensor are all the examples of tensors of rank 2. Vectors can be regarded as tensors of rank 1 and scalars as tensors of rank 0. Generalization to higher rank tensors is now obvious. A tensor Mij of rank 3 is a set of 27 quantities that transform under rotations as M-ijk equals to AIL, AJM, AKN, MLMN.
The same is true of inversion in 3 dimensions. Based on this, we have the following results. Any continuous rotation along with the inversion will also correspond to determinant of A is equals to -1. Thus, all such transformation can be divided into two classes, either pure rotation or the rotation reflections. Including the properties of physical objects under inversions along the rotation, all the tensors can be divided into two classes, either into pure tensors or into pseudo tensors. A pure scalar is one which does not change sign under inversion. A pure or true vector A is one that changes sign under inversion, that is, A vector tends to A dash vector equals to minus A vector. Now, position and velocity vectors are both examples of pure vectors. A pseudo vector or an axial vector B is one of which does not change sign under inversion, like B vector tends to B dash vector equals to B vector. Now, the angular momentum is an example of an axial vector. In fact, given two pure vectors A and B, their cross product A cross B is an axial vector. So, A vector cross B vector tends to A dash vector cross B dash vector equals to minus A dash. Angular momentum is an example of an axial vector. In fact, given two pure vectors A and B, their cross product A cross B is an axial vector. So, A vector cross B vector tends to A dash vector cross B dash vector equals to minus A vector cross minus B vector equals to A vector cross B vector. Tensors of even order do not change sign under inversion. Those of odd order do. For pseudotensors, the behavior is just the opposite.
Now let us study about the pseudotensors. Certain further properties of the transformation coefficients are interesting. Let us take the determinant of both sides of A transpose A equals to I. Then we get determinant of A transpose A is equals to determinant of A transpose into determinant of A equals to determinant of A square is equals to 1, which implies that determinant of A is equals to plus minus 1. For identity transformation, determinant of A is equals to 1. Rotation is a continuous transformation which implies under rotation determinant A which changes continuously. This implies that determinant of A equals to 1 under any continuous rotation. For a reflection in a plane, say the z equals to 0, plane x dash equals to x, y dash equals to y, z dash equals to minus z, which implies that A is equals to 1, 0, 0, 0, 1, 0, 0, 0, minus 1, which implies that determinant of A is equals to minus 1. Students, now let us play with the indices. For true vector under inversion, A vector tends to A dash vector which is equals to minus A vector. For pseudo vector under inversion, B vector tends to B dash vector equals to B vector. Tensors of even orders do not change sign under inversion, those of odd order do. For pseudotensor, the behavior is just the opposite. So now given two vectors A vector and B vector, we can make a tensor of rank 2, that is Tij equals to Ai Bj, T dash Ij is equals to A dash I, B dash J equals to Aik, Ak, Ajl Bl equals to Aik, Ajl into Ak Bl equals to Aik, Ajl Tkl. If we contract the two indices, there are no free indices, and so we get it is a scalar. So T dash II is equals to Aik Ail Tkl equals to del Kl Tkl equals to Tkk. On contracting two indices in a tensor of any rank, we obtain a tensor of rank lower by 2. A second order tensor in many ways is akin to a 3 cross 3 matrix. Symmetric tensor Tij is equals to Tji. Antisymmetric tensor Tij equals to minus Tji. The trace of tensor is represented by Tii. Now let us study about the Kronecker delta and permutation symbols. Two tensors hold a special place in tensor analysis and permutation symbol. Kronecker delta, a symmetric tensor of rank 2, del I j is equals to 1 if I is equals to j, and 0 if I is not equals to j. Permutation symbols or permutation tensors or Levi-Civita symbol, a completely antisymmetric tensor of rank 3. The components are epsilon 1 2 3 equals to epsilon 2 3 1 equals to epsilon 3 1 2 equals to 1 and epsilon 2 1 3 equals to epsilon 1 3 2 equals to epsilon 3 2 1 equals to minus 1 or epsilon ijk is equals to 0 if all three or any two indices are equal. So it can also be written as epsilon ijk equals to 1 by 2 into I minus j into j minus k into k minus I. So epsilon ijk is equals to epsilon jkl equals to epsilon kij or epsilon ijk equals to minus epsilon ikj equals to minus epsilon jik equals to minus epsilon kji. On using these definitions and properties of Kronecker delta, epsilon ijk equals to epsilon lmn del il del jm del kn equals to del I1 into del J2 del K3 minus del J3 del K2 minus del I2 whole into del J1 del K3 minus del J3 del K1 plus del I3 into del J1 del K2 minus del J2 del K1, which is further equals to determinant del I1 del J1 del K1 del I2 del J2 del K2 del I3 del J3 del K3 equals to determinant of del I1 del I2 del I3 del J1 del J2 del J3 del K1 del K2 del K3. On using the property that determinant AB is equals to determinant A into determinant B, epsilon ijk into epsilon lmn equals to determinant del I1 del I2 del I3 del J1 del J2 del J3 del K1 del K2 del K3 into determinant del L1 del M1 del N1 del L2 del M2 del N2 del L3 del M3 del N3 equals to del I1 del I2 del I3 del J1 del J2 del J3 del K1 del K2 del K3 into determinant of del L1 del M1 del N1 del L2 del M2 del N2 del L3 del M3 del N3. The first term of the multiplied matrix is del I1 del L1 plus del I2 del L2 plus del I3 del L3 equals to del IL, which implies that epsilon ijk epsilon lmn equals to determinant of del IL del IM del IN del JL del JM del JN del KL del KM del KN. For special cases, when two indices are equal, say k equals to n, epsilon ijk into epsilon lmk equals to del il del jm minus del im del jl. Dot product a vector dot b vector is equals to ai bi. Cross product a vector cross b vector is equals to epsilon ijk aj bk. Vector identities. Many of the vector relations can be proved more conveniently by using the tensor notation. So let us, as an example, consider a vector cross b vector cross c vector whole with indices I equals to epsilon ijk aj epsilon klm bl cm is equals to epsilon ijk epsilon klm aj bl cm equals to epsilon kij epsilon kln aj bl cm, which is equals to del il del jm minus del im del jl whole into aj bl cm equals to aj bi cj minus aj bj ci equals to A vector dot C vector into B minus A vector dot B vector into C whole with indices I. This implies that A vector cross B vector cross C is equals to B vector into C vector dot A vector minus C vector into A vector dot B vector. The differential operator. So let us see first gradient, where del phi with indices I is equals to del phi divided by del xi. Divergence, del dot A vector is equals to del ai by del xi. Curl, del cross A vector with indices I is equals to epsilon ijk into del ak by del xj, and Laplacian, del square phi is equals to del square phi by del xi del xi. The differential operator is indeed a vector. So xi is equals to aji x dash j, which implies that del xi by del x dash j is equals to del aki x dash k divided by del x dash j equals to aki into del jk equals to aji. If T is a tensor of any rank, then del dash I T is equals to del T by del x dash I equals to del T by del x1 into del x1 by del x dash I plus del T by del x2 into del x2 by del x dash I plus del 3 by del x3 into del x3 divided by del x dash I equals to del T by del xj into del xj by del x dash I, which is equals to aij into del T by del xj, which is equals to aij del jt, which implies that del dash I is equals to aij del j. The Kronecker delta and permutation symbol as tensors. We have so far defined Kronecker delta and permutation symbol as simply that as object having specific components. But these are indeed tensors in the sense they have the required transformation properties under the rotations. So to see this, del dash ij is equals to aik ajl, del kl is equals to aik ajk equals to del ij, which implies that it is a tensor of rank 2. Epsilon dash ijk is equals to ail, ajm, akn, epsilon lmn, and epsilon dash jik is equals to ajl, aim, akn, epsilon lmn is equals to ajm, ail, akn, epsilon mln equals to minus ajm, ail, akn, epsilon lmn equals to minus epsilon dash ijk. Similar results follow for other indices. It follows from these symmetrics that epsilon dash ijk is equals to k epsilon ijk. To determine k, put I is equals to 1, j equals to 2, k equals to 3, so that k is equals to epsilon dash 1 to 3 equals to a1l, a2m, a3n, epsilon lmn equals to determinant a equals to plus minus a, which implies that epsilon dash ijk is equals to plus minus epsilon ijk. Hence, it is a pseudo-tensor of rank 3. Isotropic tensors. An isotropic tensor is one that has the same components in all rotated frames of reference, that is Tijk is equals to T dash ijk and so on. Rank 0. All scalars are isotropic since T dash equals to T for tensors of rank 0. Rank 1. There are no non-zero isotropic tensors. For first tensor to be isotropic, A dash I is equals to aij ak is equals to ai, which implies that aij is equals to del ij, which is just like the identity transformation. Rank 2. Kronecker delta is the most general isotropic second rank tensor. Let us see the proof. Let T be a second rank isotropic tensor such that T dash is equals to T. Consider a rotation of 90 degree about z axis which is given by determinant 0, 1, 0, minus 1, 0, 0, 0, 0, 1. So this implies that determinant T dash 1, 1, T dash 1, 2, T dash 1, 3, T dash 2, 1, T dash 2, 2, T dash 2, 3, T dash 3, 1, T dash 3, 2, T dash 3, 3 is equals to determinant 0, 1, 0, minus 1, 0, 0, 0, 0, 1 into T 1, 1, T 1, 2, T 1, 3, T 2, 1, T 2, 2, 2, 2, 3, T 3, 1, T 3, 2 into T 3, 3 into 0, minus 1, 0, 1, 0, 0, 0, 0, 1, which is equals to determinant T22 minus T21 T23 minus T12 T11 minus T13 T32 minus T31 T33, which implies that T11 equals to T22, T13 equals to T31 equals to T23 equals to T32. Similar rotation about y-axis gives T11 equals to T33, T12 equals to T21 equals to T23 equals to T32 equals to 0. All the diagonal elements are equal and non-diagonal 0. Here, the most general isotropic tensor of rank 2 is K del Ij. Now let us see the physical significance of isotropic tensor of rank 2. An isotropic tensor behaves much like a scalar. Consider, for example, the conductivity tensor. In an anisotropic medium, relation between the electric field and the current density is Ji is equals to sigma Ij Ej. Since electric field and the current density are vectors, sigma Ij is a tensor of rank 2.
Here, sigma ij is the conductivity tensor. Since electric field and current densities are vector, it follows that sigma ij is indeed a tensor of rank 2. An isotropic medium has the same properties in all directions and hence we expect sigma ij to be isotropic too. Sigma ij equals to sigma delta ij. Substituting in the above equation, we find that j vector is equals to sigma e vector. Now we recover the conductivity relation for homogeneous medium.
Rank 3. There is no true tensor of rank 3. The most general isotropic tensor of third rank is the pseudo tensor, that is K epsilon ijk, the permutation tensor. Rank 4. The most general isotropic fourth rank tensor is A del ij del kl plus B del ik del jl plus C del il del jk. We skip the proof of ranks 3 and 4, which is straightforward but too long.
So students, let us summarize what we have learnt in this module. In this module, we have developed a new perspective for the idea of vectors which are related to the properties of physical quantities under rotation. We have introduced the so-called tensor notation, which is a big help in the study of rotational properties. Next, we have introduced and explained with examples the Einstein summation convention, which simplifies the formalism even further. We have then defined vectors from this new perspective of properties of physical quantities under rotation in the three-dimensional physical space. We have then generalized the idea of tensors of second and higher order ranks and explained how scalar and vector are tensors of rank 0 and 1 respectively. Next, we have further classified physical quantities on the basis of their behavior under inversion of the coordinate axis and introduced true and pseudo tensors. In this tensor or index notation, the indices play a very important role and we have demonstrated how playing around with indices may lead to significant results. Next, we have formally introduced two very special tensors, the Kronecker delta and the permutation tensor, and have discussed their useful properties. Next, we have written down certain vector identities and demonstrated how the tensor methods greatly simplify the derivation of such identities. Next, we have proved that Kronecker delta and the permutation tensor that were introduced are indeed tensors of rank 2 and 3 respectively. Finally, we briefly discussed the idea of isotropic tensors and described isotropic tensors of rank up to 4. Thank you.